Classical Newtonian mechanics is built on certainty. If you know an object's mass and its velocity, you can map its exact trajectory. But zoom in to the microscopic level, and this deterministic certainty collapses. To describe atomic behavior, we have to completely rewrite the mathematical rules using 5 specific postulates. In classical systems, properties like position and momentum exist on a continuous domain. You could measure them at any exact, infinitesimally small point. But microscopic systems operate entirely differently. Their states belong to a discontinuous, discrete domain. To capture this discontinuous reality, we have to abandon classical trajectories. Instead, we rely on mathematical descriptions called wave functions, denoted by the Greek letter psi. This necessity establishes the first postulate of quantum mechanics. The state of a quantum system is completely described by a mathematical function, psi of position and time, which contains every piece of information that can possibly be extracted about that system. A mathematical function alone does not give us a physical location. Physicist Max Born provided the translation. If you take the squared absolute value of the wave function, the resulting quantity gives you the exact spatial probability density of finding a particle at a given point in space and time. We are no longer tracking exactly where a particle is. We are mapping the likelihood of where it could be. Postulate 1 establishes this probability wave as the mandatory foundation for all quantum calculations. A wave function cannot just be any arbitrary mathematical expression. To act as a valid probability distribution, it must be well-behaved. It must be single-valued, meaning a particle does not have multiple contradictory probabilities at the same position. It must also be continuous and finite everywhere. There is an additional, strict physical requirement: normalization. If you integrate the probability density over all possible space, the result must equal exactly 1. This ensures there is a 100% chance the particle actually exists somewhere in the universe. To test how these axioms work in practice, we use a standard conceptual model, a single particle trapped in a one-dimensional box. We will examine its lowest possible energy configuration, known as the ground state. This graph shows the probability distribution curve for our ground state particle in a box of width A. Our goal is to calculate the exact numerical probability of finding the particle strictly in the left half of the confinement, between x equals 0 and x equals a over 2. We set up the integral of the squared wave function, bounding the evaluation from 0 to a over 2. We substitute in the established ground state wave function, which is the square root of 2 over a, multiplied by the sine of pi times x divided by a. By applying a standard trigonometric identity to handle the sine squared term, the complex integration simplifies. Evaluating the resulting expression at our specific boundaries yields exactly 1/2, confirming a 50% probability. The wave function acts as a rigorous mathematical engine. It takes an abstract, unobservable quantum state and processes it into a precise, verifiable physical probability. Because our particle exists as a probability distribution rather than a point with a definitive trajectory, standard classical formulas fail. We cannot simply calculate kinetic energy as momentum squared divided by twice the mass. Postulate 2 resolves this by dictating that for every measurable physical property, such as position, momentum, or energy, there is a corresponding linear Hermitian operator in quantum mechanics. To construct the quantum operator for kinetic energy, we take the classical expression and replace the momentum variables with their exact quantum counterparts. Momentum becomes a differential operator involving a spatial derivative and h-bar. H-bar is the reduced Planck constant, a foundational unit of quantum action. Substituting this differential operator directly into the classical formula yields our working quantum kinetic energy operator. Postulate 3 determines how we actually use these operators. It states that when you execute a measurement on a quantum system, the only possible outcome is one of the distinct eigenvalues associated with that specific operator. This relies on the eigenvalue equation. When you apply an operator to its corresponding eigenfunction, the mathematical execution returns the exact same function, multiplied by a constant. That constant is the eigenvalue. It represents the actual physical number you will read on a laboratory instrument. We specifically require these quantum operators to be Hermitian. A Hermitian operator possesses a mathematical structure that guarantees its eigenvalues will always be real numbers, rather than complex or imaginary ones. This is a non-negotiable requirement, as physical properties like mass and kinetic energy must be real values. In the quantum realm, passive observation does not exist. To extract real-world data, we must actively apply a mathematical operator to the state function. This operation is straightforward when a particle occupies a single defined energy state, but often the quantum system exists as a mixture, meaning the state is not a pure eigenfunction of the operator we are trying to use. Postulate 4 addresses these mixed conditions. It defines the superposition state, where the total wave function is a linear combination of multiple distinct eigenfunctions, each multiplied by its own complex coefficient. If we measure the energy of this combined state, the system does not output a smeared average energy reading. The measurement will definitively collapse into one of the discrete allowed eigenvalues, such as E1 or E2. The likelihood of getting either result is derived via the expectation value. By taking the squared absolute modulus of each complex coefficient, we extract the exact percentage probability of measuring that specific eigenvalue. Here, squaring our respective coefficients gives us a 75% chance of measuring state 1 and a 25% chance for state 2. An expectation value does not predict a single guaranteed physical outcome for one isolated experiment. It computes the mathematically weighted average of what you will measure if you repeat the exact same experiment an infinite number of times. We can deploy this expectation framework to calculate a counterintuitive physical reality for our one-dimensional particle in a box. We will determine its average expected momentum in the ground state. We set up the expectation integral over the total width of the box. We sandwich the momentum operator, which Duyckxen's the spatial derivative, directly between the complex conjugate of the wave function and the original wave function itself. As the derivative triggers visually, the operator executes a spatial derivative on the right-hand wave function. This mathematically transforms the original sine function into a cosine function, pulling out a constant to the front of the integral. This leaves us integrating the product of sine and cosine. By applying trigonometric identities and evaluating the combined function at the boundaries of the box, the terms cancel out perfectly. The entire mathematical expression collapses to exactly zero. The mathematics formally verify the physical intuition. Because the particle is tightly confined within the walls of the box, at any given microsecond, it has an exactly equal probability of moving to the right or to the left. These opposing probabilities average out, leaving a net expected momentum of zero. The first 4 postulates dictate how to describe and measure a quantum state at a frozen instant in time. Postulate 5 introduces the mechanics of how this probabilistic system actually moves forward through time. Time evolution is governed entirely by the time-dependent Schrödinger equation. This formula directly links the total energy of the system on the left side with the first derivative of time on the right. The central component here is the Hamiltonian operator. While it acts as the observable operator for total energy, it also serves as the mathematical generator that pushes the wave forward in time. If the potential energy of the system is strictly independent of time, we can execute a mathematical technique called the separation of variables. This cleanly cleaves the full wave function into 2 distinct parts, a fixed spatial component and an oscillating temporal component. These specific energy eigenfunctions are known as stationary states. If you calculate the spatial probability density for a stationary state, the time variables mathematically cancel each other out. The probability distribution of finding the particle in a specific location remains completely unchanged as time passes. This yields a profound structural contradiction. While a single measurement of a quantum system is entirely probabilistic, the mathematical evolution of the underlying quantum wave over time is strictly and elegantly deterministic. No single equation can process the microscopic world alone. We must chain these 5 axioms together into a cohesive operating framework. Postulate 1 dictates that the physical system must be defined entirely through a well-behaved probability wave. Postulates 2 and 3 require us to apply a Hermitian operator to that wave to extract discrete, real-valued measurements. Postulate 4 uses expectation values to average the specific measurement probabilities of mixed superposition states. and Postulate 5 deploys the Hamiltonian operator to deterministically evolve the entire probabilistic system forward in time. Ultimately, classical mechanics merely describes what is. Quantum mechanics provides the mathematical operating system to orchestrate what is probable, forming the absolute bedrock of modern physical chemistry.